we're going to get started. And it is my great pleasure to introduce Becky Bendick, who is an associate professor of geophysics at the University of Montana. Her bachelor's degree in biology and geology is from Yale University, where she was also a sailor. And her PhD in geophysics from the University of Colorado here in Boulder. Her primary research interests include continental deformation, tectonics, and the earthquake cycle. Aside from her research, she works hard to help convey geologic hazards information to at-risk communities worldwide. She teaches tectonics and geophysics, as well as critical thinking, scientific literacy, and numeracy. She dabbles in the ethics of scientific discoveries. I believe this is a self-description. And she is a member of UNAVCO's board of directors and an active participant in UNAVCO's community. And for those of you who don't ponder the effort that goes into these board meetings as you wander by for over the course of several days, we have a great debt to the community members who are willing to step forward and take the fiduciary responsibility of running UNAVCO and guiding us and helping us set direction. Pete Lefeminot, chair of the board, is also here, and I guess Paco got away. But anyway, okay, so let's just thank these people for the many hours that they give to ensuring our viability as an organization. Thank you.
You make our job very, very easy.
Yeah, so I was primarily going to use my role on the board as an excuse for anything totally idiotic I might say in the next 40 or so minutes. But barring that, thank you very much for inviting me to give the science seminar. I'm actually vastly more comfortable giving talks like this to people who don't know what I'm talking about, so this is a little scary for me to do, but I hope that I've picked a topic that will be enough of interest to you to stimulate some discussion and not necessarily overlapping the things that you guys think about every single day. So I want to talk about the answer-ish to this question of how sensitive surface velocities and surface displacements are to the underlying dynamics of tectonic processes. And in the interest of clarity, I want to use 3 words throughout this talk in very specific and very narrow ways. Those are kinematics, which I'll use to mean a description of what moves where and how fast. Mechanics, which I'll use hopefully consistently to mean the material properties of the things we're talking about, which in this case is predominantly the lithosphere, although at times it may just be the crust. And then dynamics, and by dynamics, for the purposes of this talk, I really mean the balance of forces and torques on those earth materials. And I'll do my very best to use those words in those ways and in those ways only, and hopefully that will help. So this question of the relationship between tectonic processes, hang on. Yes. Okay. What did you do, though?
That was that turn.
Okay.
But now it probably works a while. It's just fun.
Okay, great. So this question of the relationship between how tectonics work and what moves around in tectonics really has its origins in the beginning of the theory, if not before. So the fundamental observation of tectonics, even before it was a quantifiable theory, is one of motion, and of motion of surface features. So fundamentally, Wegener's argument was based on the motion of pieces of the surface of the Earth, in this case, South America and Africa. And in the early codification of plate tectonics as a more quantitative theory, it's fundamentally these observations of displacement over time, which we conveniently give the name velocity, that make this a self-consistent and basically quantitative theory. And so immediately upon the proposition of pieces of the Earth's lithosphere moving relative to each other, the task at hand was to place constraints on that. And really, you might argue that the full realization of plate tectonics as a theory came very swiftly after the initial proposition in the form of a table of numbers. And what this is just a compilation based on a set of observations of displacement at the surface of the Earth of a complete description of the kinematics of these plates. And because of their rigidity and because of the localization of their relative motion on plate boundaries, we can condense the whole notion of the surface moving around down to a set of Euler vectors. But I think it was pretty quickly unsatisfying to say that a full description of surface kinematics is sufficient to our understanding of the behavior of the lithosphere, because immediately following this careful formulation comes the extrapolation of the kinematics to a more dynamic understanding of the Earth. And that comes in the form of thinking, okay, if these bits and pieces are moving around, why? Why are they moving around, and what is the relationship between causation or force balance or dynamics and their motions? And so quite early on, there were some nice attempts made to, first of all, list all the possible forces and torques on plates, and then compare them to velocities. And so this lovely paper shows here, I think fairly convincingly, that there isn't much correlation between the surface area of plates and their velocity, or the length of ridges on plate boundaries and their velocities, but there is a strong relationship between the length of subduction boundaries and the velocity of plates. So we immediately now go from this notion of straight kinematics, describing what's moving where and how fast, to using that as a window into understanding why these motions are happening. The problem is, though, of course, this little key question, or this little key statement down here, that these plates are not accelerating. So we know from basic physics that that must mean that all of the forces and torques on them are effectively balanced, or at least extremely close to being balanced. So actually quantifying what these underlying forces and torques are is essentially impossible, because you have a long list of things which add up to zero, and you can't really figure out in which proportions are they canceling each other out, or exactly what the absolute value of any particular one of these forces or torques is in the system. And so it's assumedly these small kind of perturbations or anomalies that to this perfect equilibrium that excite plate motion. But fundamentally, and Peter Molnar never fails to remind me, that there are no driving forces to plate tectonics. Tectonics is best described as an equation of state, so these things are at equilibrium. However, observations of plate motions are still used to constrain dynamic models for why tectonics happens and how it happens, and which of these forces and torques are most important to both conveying heat out of the interior of the Earth and displacing parts of the lithosphere. So this is, of course, a famous paper where the argument for slab suction as an important force is made based solely on a fit to surface observations of tectonic kinematics, so surface observations of velocities. And even the most kind of cutting-edge new contributions to tectonic dynamics research, mainly through numerical simulations, are predominantly constrained by surface observations of kinematic fields, so displacements and velocities. This is out of Mike Gurness's group, and and they tune their dynamic simulations to reproduce the kinematic field at the surface. So one thing to point out that's quite, I think, critical to this discussion for the rest of this talk is that during the early development of tectonics, both as a kinematic and a dynamic theory, the vast preponderance, if not 100% of the kinematic indicators from the surface came from oceanic settings. So the strike of transform faults and the width of magnetic stripes in the seafloor. And oceanic lithosphere has particular properties that make those generalizable. So observations of kinematics from the ocean are relatively easy to then apply to a whole large lithospheric object, which is made of oceanic lithosphere. And this is also true even for these very new tectonic dynamic simulations. They're predominantly seeking to reproduce the behavior of oceanic lithospheric plates. But it's, and this is, historical because of the number of kinematic observations from the ocean, but it's also because of the mechanics of oceanic lithosphere. So suppose then that along to the story comes a whole bunch of new kinematic indicators, not magnetic stripes on the seafloor anymore or transform fault strikes, but point measurements of displacements over time, so velocities, so kinematics, that are now not dominantly in the oceans, in fact, essentially not at all in the oceans, but dominantly on the continents. How might we respond to those? Well, the obvious thing to do is to add them into the bucket and say, okay, now we don't have this biased set of kinematic indicators. We have a global swath of kinematic indicators, some from the oceans, some from the continents, but they're essentially all vectors. We'll treat them the same way, and then use this same idea about the overall kinematic field as a constraint for the underlying dynamics and force and torque balance for the lithosphere. But this neglects something absolutely critical that shows up right away in the terrestrial geodetic data sets, which is that the GPS indicators on continents show that the continents are much less plate-like, somehow fundamentally, than the oceanic lithosphere is. So we have this difficulty that there are two sets of flavors of observations. They're actually very seldom overlapping one another in space, and they may in fact be sampling quite different behavior. And so although we can kind of now say we have a global sample of the kinematic field, it's worth thinking, I think, quite carefully whether or not that kinematic field is sufficiently sampling the same thing as to homogeneously apply constraints on dynamics in the way that they've been used to look at the dynamics of the oceanic lithosphere. And I'm going to use the rest of this talk to argue to you that we may, in fact, be able to do this, but not without a little bit of careful consideration first as to whether or not there are additional contributions to the kinematic field in continental settings that do not contribute in the same way to the kinematics of oceanic settings. And we can tell that this is potentially a problem by looking anywhere in continents, but everyone's favorite model test is the Tibetan Plateau. So supposing that we have a basically arbitrary set of kinematic indicators for some region that we know is affected by tectonics and is in a continental setting. Well, can we then use those to, first of all, simplify the kinematic field in the way that Minster and Jordan took a whole bunch of indicators from the oceans and collapsed it onto a short list of Euler vectors? And then if we can do that, then can we use that understanding to infer some important things about the basic balance of forces that excites plate tectonics in the first place? Well, tricky, because you can take this velocity field and you can fit it with pretty much identical statistical confidence by using a bunch of blocks, which preserves this kind of idea of the plate tectonic approximation of rigid entities separated by narrow boundaries, or by thin viscous sheets, or by gravity flows, or by kind of the latest and greatest super sexy composite laminate multi-layered finite element model. So essentially, all of the approximations we might make to simplify the kinematic field can satisfy the constraints of the surface observations equally well. And you might say, okay, well, that doesn't matter. We can just pick some arbitrary realization of the kinematic field and then say, okay, this is just what we're going to pick to kind of turn a bunch of vectors into a simpler mathematical state, and it doesn't matter why. The problem is that each of these realizations of the kinematic field actually has absolutely fundamentally different and incompatible implications for the underlying dynamic force balance. So, for example, with some of these simulations, they require or they imply that basal attractions are very important in Tibet, whilst others imply that basal attractions play no role. And for some of these, the boundary velocity condition is the primary sort of unbalanced force that excites the initial velocity of these things, and for others, it's gravitational potential energy. So if we want to actually understand the dynamics, we have to, for continents, take the important step of quantifying the role of the mechanical properties of the continental lithosphere. So I like to think of this as though the continental lithosphere acts as a filter. And if you want to think of it as the kind of forward problem, you have an input of a bunch of forces and torques. They pass through the filter of the continental lithosphere, and then out come surface velocities. And so if you eventually want to do this problem in the way that we do in the ocean, we take the observations of surface velocities, use those to constrain the balance of forces and torques, then we have to characterize this filter. Is it a lossy filter? Is it letting certain kinds of information through and other kinds of information not? Or is it preserving the full set of parameters? Is it passing through all the information we would need to understand the underlying dynamics? And so now I'm going to take you through two different approaches to characterizing the filter, or at least saying how bad is that filter, that I've been working on with my friend Lucy Flesch for quite a while now. And I kind of shorthandedly named them the forward approach and the inverse approach. This isn't really fair because the forward approach is properly a forward approach, and the inverse approach is actually just a kind of arm-wavy thought experiment of the kind I particularly love. But so I'll take you through the forward problem first. And the idea there was to actually just say, okay, we know that we have a range of plausible mechanical scenarios for continental lithosphere. And this is just a compilation from an older paper by James Jackson that shows, that as you vary the chemical composition of the crust in the mantle lithosphere and also the amount of water in the crust in the mantle lithosphere, you can have a range of strength profiles. And you'll notice this is stress, but these can also be, by leveraging the Stokes analogy, these could also be thought of as effective viscosity profiles. You can have a range of distributions of strength, and I'm actually going to stop using strength and use the word competence, because mechanical competence can be either strength of an elastic material or stiffness of a viscous material. So you can have a range of competence profiles in the continental lithosphere, and it's pretty clear that that same range of competence profiles does not exist for the oceanic lithosphere. So competence in the oceanic lithosphere is fundamentally a continuous function, so that it can be approximated as a single sheet or a beam. And so then once we took a look at this, Lucy and I decided to kind of generalize the range of options into 4. One is a continuous competence profile, like you would expect for oceanic lithosphere, just thicker, because everybody knows that continental lithosphere is thicker than oceanic lithosphere. Then 3 heterogeneous competence profiles, one in which the crust is the strongest part of the lithosphere, one in which the mantle lithosphere is the strongest part of the lithosphere, and a final one where you have some kind of crazy arbitrary distribution of competence in several different layers of continental lithosphere. And we thought, okay, well, what happens if we take these mechanical profiles and apply absolutely identical boundary and body conditions to volumes that have those characteristics? And this is what happens, and I blame Lucy. This is the most dense figure of all time. But let me just take you through it bit by bit. So here are the competence profiles as a function of depth for each model set next to them. Every single one of these model runs, as I said, have absolutely identical boundary conditions and body conditions. So the boundary conditions are that this boundary moves at a steady velocity towards this back boundary, which is fixed. And then these gray or paler gray circles are a Gaussian-shaped topography in isostatic equilibrium bunged into the middle of the volume, so that we have some topography and we have some velocity boundary conditions. And then these slices are the velocity field at 3 layers in the lithosphere. This is the surface, this is in the lower crust, and this is at the bottom of the model. And so what you can see here is for a continuous competence profile, the velocity field through the lithosphere is the same everywhere. So this is actually important because this means that what you measure at the surface gives you all of the information about the velocity, displacement, strain, whatever you choose to measure through the whole lithosphere. So this is tantamount to saying that a continuous competence profile here is a lossless filter. The lithosphere is not modulating the amount of information available at the surface in any way. It's continuous through the lithosphere, so measuring at the surface is as good as measuring anywhere else. And since we happen to be at the surface, awesome. That's my first choice of where to measure. If we have a weak lower crust, but it's within 2 orders of magnitude of the strength of other parts of the lithosphere, so the discontinuity in the competence is small, we actually preserve that relationship. So the surface field is highly correlated, if not identical, to the velocity field in the middle crust and in the bottom of the lithosphere. So we're not losing information as the dynamics are kind of forced through the response of a material. I should also say that we tuned these absolute values so that all of these lithospheric models have the same average effective viscosity, so they have the same Argon number, if any of you are familiar with that as a measure of the kind of mechanical properties of lithosphere. But if you drop the strength or the competence of the lower crust below that 2 orders of magnitude threshold, you can see pretty easily here that the surface velocity field is not the same as the velocity field in the middle crust, and it's actually not the same as the field at the bottom of the lithosphere either. So what this means is that this is the first of our scenarios where measuring at the surface does not give you all of the information about the deformation modes going through the lithosphere. And so somehow you're losing some basic information about either the mechanical properties or the dynamic setting. And you can see that really clearly in these last two runs. So with the strong crust, what you see again is that there's a decorrelation with depth in the lithosphere. And we thought the most interesting thing is what you capture at the surface is essentially only the boundary condition. So the strong crustal model filters out all of the information about the body conditions. So all of the GPE, gradients in GPE are filtered out by a strong crust relative to the competence of the mantle lithosphere. And the opposite is true if you have the most competence in the lithosphere hosted in the mantle lithosphere. In that case, the surface field filters out much of the velocity boundary condition, and you recover dominantly the gradients and the gravitational potential energy in the surface observations. And so this forward model gives us a way of at least kind of quantifying the extent to which the continental lithosphere is a lossy filter, and ideally the circumstances under which those losses are large versus small. And so we actually could use that to say that we'll classify the kind of modes of understanding continental tectonics according to their corresponding competence distribution in the lithosphere. So classic tectonics, either the case of true plates or thin viscous sheets, correspond to the scenario where you're recovering all of the information about the velocity field through the whole lithosphere at the surface, and that's essentially because there's continuity in the competence with depth in the lithosphere. Block-like models and block-like behavior, which is highly sensitive to velocity boundary conditions, correspond to a scenario where you have the most competence in the lithosphere in the crust, and these respond dominantly to velocity conditions. And then gravity flow models, which is sort of the extreme opposite of block-like models, correspond to a scenario where the highest competence in the lithosphere is in the mantle lithosphere, and these are dominantly sensitive to gradients and gravitational potential energy. And with these multi-layered systems, what turns out to be the critical parameter in them is the competence contrast from layer to layer. So if that's kept within that sort of 2 orders of magnitude bound, you can reduce these problems to one of these others, which is nice. But if there are large competence discontinuities in the material, if the discontinuity is very large, then the deformation at the surface is a linear sum of the deformation field in each layer. If the competence is intermediate, this is sort of worst possible scenario, because the surface velocities are a harmonic and not even necessarily the first harmonic of the combination of all of the deformations in each of the layers. So that gets to be pretty hard to decipher. And you might ask the next question, or we did, which is, do all of these actually occur on Earth in continental senates? And I think there's a strong argument to be made that they do, because we can see actually that in the 3 kind of most well-studied settings of continental tectonics, we have 3 different observations of a balance between body forces and boundary forces playing a leading role in exciting the surface velocity field. So for Tibet, sort of regardless of what approximations you use to fit the velocity field, you see you need a combination of boundary velocities and gravitational potential energy contributions to reproduce the velocity field. And so we would argue that means, or that implies, that there's probably a continuous competence curve for the lithosphere in the Tibet region. If you look at, I do next, the basin and range, what you see here is that at least at intermediate wavelengths and all the way out to quite long wavelengths, the dominant mechanism required to reproduce this velocity field is the boundary velocity condition on the San Andreas Fault. And gravitational potential energy certainly plays a role, but it's relegated, or it's of lesser weight in reconstructing the velocity field than the boundary condition here. So we would argue that suggests that a lot of the competence in the western U.S. is hosted in the crust, and that's consistent with seismic observations of a strongly attenuated and warm mantle lithosphere beneath the basin and range. And then if you look at East Africa, you dominantly see in the velocity field, and admittedly this is quite sparse, but we're working on it, that gravitational potential energy gradients or topographic gradients produce the largest contribution to the velocity field, at least south of the Afar. And so we would infer then that that's consistent with having much of the competence in Africa hosted in the mantle lithosphere. And then as you get to the Afar, you kind of revert to this block-like model. And again, that's consistent with seismic observations that demonstrate that the mantle lithosphere is either highly attenuated or entirely lacking in the northernmost East African tectonic system. Okay, so we can kind of work back and forth with this forward model to say, well, this is the characterization of the continental lithosphere as a filter, and actually probably all of these different modes are relevant to particular Earth settings. And the nice thing about doing this exercise is then it informs which choice of models we might want to choose. So all of these have been realized in one or more or 150, I don't know, different kinds of numerical simulations. And so it makes sense if you're going to think about continental tectonic dynamics then to choose a model realization that's consistent with your understanding of the distribution of competence in the lithosphere. And this happens to be all of the things that have been proposed for Tibet. We would argue that actually the thin viscous sheet model is the most appropriate choice, based both on the kind of power in the surface velocity field and how it balances between these two different contributions, but also based on some other a priori and ancillary information about what the competence structure beneath Tibet might be. And that brings me to my inverse arm-wavy thought experiment. So all of the pictures I showed you before were this Tibetan velocity field, a bit decimated, cut off here at the Karakoram Fault. So the latest thing we've actually been working on is thinking about how to properly explore this velocity field, because we know that topographic gradients are an important contributor. So by stopping the velocity field as an input or a constraint to numerical simulations in a place that doesn't match up with the edge of the high topography, you're artificially creating a boundary here that skews the response of the modeled velocity field. So we actually took all of the observations from older Tian Shan studies and then a bunch of our recent work in the Pamirs and the Hindu Kush and the Pakistan Himalaya and added those in to the velocity fields of interest and took a look at what that actually does to our understanding of the whole system. This is a cool extra way of studying how dynamic contributors are manifest at the surface, because this region that I'm showing you now that we've added the Pamir to it is absolutely well known separately from this discussion to have very different dynamics along strike, if you can call it strike for such a curvy thing. Specifically, in the far west here, a whole bunch of really cool recent work, mostly out of GAFZ, shows that there's a very distinct, intact Benioff-style slab subducting underneath the Pamir. And so there's a structural source of additional forces and torques to contribute to the dynamic balance that is certainly not present in central Tibet. So there's plenty of seismic work here that shows there isn't a slab there. It doesn't host earthquakes, so maybe there's like a seismic velocity anomaly, but it's not a proper slab dragging stuff around and pulling things down under. But there is still a thick lithosphere. And then farther to the east, we have yet a different set of sort of fundamental conditions on the system, which is there's good seismic and other evidence to suggest that there's quite a strong layer of material in the lower lithosphere that's stiff, and then you have a softer body of material moving out over the top of that stiff layer. So if you want to think about this large region now as a perfect, beautiful, controlled experiment for whether or not dynamics get through the continental lithosphere to the surface, this is it. Because we have a known, really basic, zeroth order difference in the dynamics from here to here to here that we know separately from observations of the velocity. So then the big question is, do you have to account for those differences in the underlying dynamics in order to reproduce the surface velocity field? And I'm going to say to you right now, before I spill the beans in the next slide, if you don't have to account for these really fundamental structural and dynamic differences from place to place in this system, then that means the information about the dynamics is lost from the bottom of the lithosphere to the surface velocity field. Because we know they're there, but if they don't affect the surface velocity field, then the surface velocity field is not preserving robustly information about those heterogeneities in the underlying dynamics. Okay, so guess what? This is a thin viscous heat model that's the best fitting model to the full suite of velocity observations. And the thing about the thin viscous heat model is you can't vary it laterally in terms of its spatial boundary conditions or internal structure. So there is absolutely no way whatsoever to include things like the Pamir slab or the pure shear thickening of the Tibetan lithosphere or a stiff basal plate underneath this outflow here on the eastern margin of Tibet. But this actually fits. So this velocity field from the thin viscous heat model actually fits the observations of surface velocities from GPS with an RMS of 1.4, which is an order of magnitude better than any of the other numerical models. So this is a major improvement in the fit by totally taking out all of the interesting stuff in the model. So basically the only contributions to this model are gradients in the topography, so gravitational potential energy gradients, and then a convergent velocity between India and stable Siberia. And interestingly, there are a couple of places where the improvement is dramatic, even from, never mind from the other kind of numerical simulations, but even from previous thin viscous sheet models. And that is by replacing the Karakoram fault as a sort of fixed velocity strike slip boundary on the thin viscous sheet, you hugely improve the fit out here, because that fixed boundary condition on the Karakoram fault essentially forced all of the mass balance fluxes required by the shortening out to the east. But by allowing flow through westward into the Pamir, you actually fix that problem quite a bit. And the model velocities of extrusion, if you want to call it that, or whatever you want to say, sort of eastbound fluxes here, these velocities get smaller, and they get a better fit to the rotation about the eastern syntaxis by allowing this communication between the Pamir and the Tibetan Plateau. And actually, the first thing we saw when we plotted this whole velocity field, I think, is something that I would guess maybe people wouldn't have expected, is that this system is actually remarkably symmetrical. You have collapse outward of the high topography, both to the east and to the west. So you spill flux from the high Pamir into the Tajik Depression, as well as into Sichuan and the eastern margin, as well as, to some extent, into the Tarim from Tibet, but certainly into the Tarim from the Tian Shan. So that's a major improvement. Do you have a question? I'm always still talking. Ask me a question.
Question is, you said you had to impose the elevation change across the entire domain.
No, we just input the topography as it is.
Right.
Yeah.
Whatever.
Okay.
But it's built into the model.
Yep.
And then you said the boundary velocity is very important in
Here.
constraining that. But isn't also the geometry of the boundary important?
Yes, and if you want to talk about that, we can. I've done a bunch of numerical simulation on the shape of that boundary, and but it's somewhat unrelated to that. Can I defer that question till the end? Okay. I wonder, I probably don't have the right figures on my laptop anyway, but I'll wave my arms at you happily. Yeah, so where else is the fit better? Well, obviously here at the Karakoram Fault, because this velocity field is more consistent with our updated understanding of very low slip rates on the Karakoram Fault. And then obviously the fit between the model and the observations is great here in the Pamir, but that's a little bit unfair because those observations of velocity in the Pamir are relatively new anyway. So the other models that we're comparing this to didn't have access to those observations anyway. But I think it's pretty, I wouldn't say it's like completely convincing, but I think it's an interesting argument to make that we do not need to incorporate known fundamental structural differences from region to region here to get an extremely good match between the predicted surface velocities and the observations. What we, of course, do need to do is make big faults a bit weak. But if you look at this, actually, the range of effective viscosities, and this is, again, a thin sheet model, so this is the integrated effective viscosity average for the entire lithosphere, varies very little all the way from essentially the Tajik Depression to the Sichuan Basin, with the exception of making faults weak. So there is some, for sure, localization of strain or increase in strain rates around big faults. And actually, I would be quite worried if that weren't the case, because we do certainly also know that faults in the crust exist and have a fundamental contribution to the surface velocity field as we measure it with GPS. So I'm going to summarize, but that's not the end of my talk, so don't breathe a sigh of relief yet. But this seems like a good point to do this. Surface velocities in continents have strong sensitivities and a similar weight of sensitivity to both the mechanical properties of the lithosphere, in particular competence contrast, and to the underlying dynamics. And so although everybody loves to and was trained to use observations of surface velocity and deformation as a primary constraint to dynamic modeling, we should not do this unless we properly account for the mechanical contribution to the surface velocity field. And fortunately, it's not a completely lost cause, because we have some other kinds of data that can constrain the mechanical state of the continental lithosphere. And of that mechanical state, I think our critical parameter is pretty clearly based on the forward modeling, this competence continuity. So how big of a discontinuity do you have in the confidence curve? And then thinking about kind of going forward with this research, it's also perhaps sensitive to temporal variation in material properties, and that's a kind of world of continental lithosphere study that I think we've only barely begun to explore. So what do we do now? Instead, I think of inverting many global continental GPS surface velocity fields for continental dynamics. We ought to spend some time characterizing the filter a bit better. So to what extent is information passed through from dynamics to surface kinematics in continental settings? How does this vary from place to place? And how can we really put reasonable bounds on the filter parameters of the continental lithosphere? And there have been some nice contributions in this area already. The first really comes from using seismic products to estimate lithospheric thickness and lithospheric temperature, so getting a proper grip on what the geotherm looks like through the entire lithosphere for continental settings, because it's really probably temperature that's at least one of the dominant controls on whether or not we have these large competence contrasts in the continental lithosphere. And that clearly goes hand in hand with getting a better idea of the chemistry and composition of the continental lithosphere. And once we do that, I think that the entire field of rock mechanics has been sort of neglected and is absolutely critical to solving this problem in a reasonable way. So if you look through the rock mechanics literature, for deep crustal and mantle lithospheric temperature and pressures, we really only know the rheological parameters for 2 or 3 compositions of rocks. And so finding some basic understanding of how these rocks behave under these conditions, and then ideally tying that understanding to seismic observations so we can back out for real places what their likely material properties are, is absolutely critical. And there's really no good way to proceed with continental dynamics before that's accomplished a little bit better. But in the meantime, we can sort of use this balance between how much information in the surface velocity field is retained about the velocity boundary conditions versus how much information is retained about the gravitational potential from topography and crustal and lithospheric thickness, to at least give us a shortcut to which model realization is more or less appropriate for a particular setting. And I would guess that this is sort of a contentious argument to make, because maybe this idea of just looking at the relative weight of those pieces of information is a little too simplistic, but I kind of like it as a concept. And then in terms of getting around the temporal variations in mechanical properties, again, I think this is a place where a bunch of interesting research needs to be done and is happening apace. So this is observations of the post-seismic signals of displacement or velocity from the Kashmir region. And while it's extremely hard to get the material properties from surface velocities when a system is in steady state equilibrium, you can get real bounds on effective viscosity of different layers in the lithosphere when you perturb the system. So when it's out of equilibrium and moving back towards a steady state equilibrium, that is when we can actually put some numbers on these material properties from the surface velocity field. But there's an issue here, of course, that we're in only a very narrow band of the time domain. And I would guess that this is also true for looking at temporal variations, say, in the coupling across key tectonic boundaries. And I couldn't find a coupling study of a purely tectonic boundary that was interior to continental lithosphere. But coupling of continental tectonic boundaries, I think, is another place that will help us to get at some of the possible contributions to the surface velocity of temporal variations in mechanical properties. So while the take-home message is maybe slightly discouraging, that we can't just go out and measure all this cool GPS and then say, here is exactly how this system deforms and why it deforms in this way, it's also really exciting from a scientific perspective because there are tons of things we don't know, and what could be better if you're a scientist than to realize you don't know something, but you might be able to figure it out. So I will leave it at that, and we can talk about curvature of the Himalaya if you want.
I was just wondering if you wanted to say anything at all about your type 1, type 2, type 3 were matching up with a contractional, transform, and extensional boundary system. If you, is that a coincidence? Is that a fundamental aspect of it? Is it irrelevant?
I think it's a coincidence, but I guess I don't know that. I mean,
since you're associating them with, in essence, the rheological structure of the lithosphere, and since you'd expect, a colder lithosphere in a compressional environment and a hotter lithosphere in an extensional environment, I could see that there might be cause and effect there, but I was just wondering, it just struck me that it seemed like your three examples were also three different boundaries.
I actually think that is not determinative, because if you, it depends if you think that the basin and range of transform or extension.
Well, the deformation field you're worrying about, the thing you're saying you're mainly fitting is transform.
That's true, is dominant.
I worry about the basin and range as an extensional environment, but that's not the dominant thing you're showing.
But some of the other things that we've been playing around with, I don't think it matters, because if you look, say, more, let's say, qualitatively at comparing East Africa with the Himalaya and Tibet, I think that those two systems have some characteristics in common in that they both have a region of relatively localized deformation, that is the rift or the Himalayan front, and a large region of distributed deformation, which is Tibet, and in Africa, the Ethiopian highlands. And so I think they have a lot of kind of basic characteristics in common, and what is differentiating them in my type 1, type 2, type 3 is where it's the competence. I see what they're saying, like if you heat something, it's going to likely have less competence, but it wouldn't matter if the overall competence were higher or lower. All that matters is it continuous or discontinuous, and that probably isn't so dependent on boundary type. I don't know the answer, I guess. Yeah.
I guess my question then would be, the only way to get at the vertical structure of the mechanical properties of the lithosphere would be to use different types of loads with different spatial wavelengths and different temporal wavelengths.
Yes.
And when you do that and then you try to see where those loads are sensing in the system, what do you get? My sense is that it's uncertain enough or ambiguous enough that you really can't resolve it all that well.
Yes, we've toyed around with this a bit in the western United States already by looking at the velocity fields on a variable wavelength filter, basically, and looking at whether or not the sensitivity appears to change. And you're right, it's just a bit under constraint. It's a bit too non-unique to do that without additional a priori information. But the nice thing is we're not stuck in the scenario where all we have is the surface velocity field, because if that were true, this talk would end differently. It would say, we will never figure out continental dynamics because you can't. right? You can't deconvolve the mechanical contribution from the dynamic contribution only using surface velocities. But we have tons of other cool things that we can use, and I think it's going to be a matter of iterating, saying, well, look, we can rule out this competence distribution because of this observation or this. And so you have to kind of build up a composite view, and I'm sure still that there won't be only one solution that uniquely fits all the data, but we can at least try to set aside some of the debate over which end member is correct and move towards trying to understand exactly what is real in the lithosphere in terms of its material properties, and then go back to, how important is mantle traction, say. Okay. Since I handled the other one so elegantly.
I was just wondering if surface, you're talking about horizontal velocities. Does surface
certainly.
velocity buy you anything at all, or is that something you've looked at?
Vertical, you mean? You mean surface vertical velocity?
Yeah.
Probably. Yeah. Probably. And probably the time series and the processing methods are getting to the point where those will be good enough to be helpful. But as everybody knows in this room, way better than I, there are a lot of other contributors to the vertical velocity field, most of them near surface. And so, yes, I think that ultimately will probably help, but we'll have to be very certain that we're not measuring snow loading. Okay.
Well, yeah, but I mean, I was just wondering if you lose some of the ambiguity, the fundamental ambiguity. Admittedly, yeah, there's lots of problems, but I mean, people are starting to work now more with vertical geodesy.
Yeah.
And if that, because vertical motions are going to be more sensitive to the overall density structure through the lithosphere, if that might buy you something, or if it's just if it just turns out that it's an incompressibility phenomenon where it's, where materials converging, you get uplift, and where it's diverging, you're going down, you'd gain nothing. So. Yeah,
I mean, I think that as you well know, one of the dynamic contributors that's been argued as a really important player in continents that we never see in oceanic lithosphere are sort of downwellings or Greg Hausman-ish drops and that sort of thing. And one of the ways this approach could be used is once we do a better job of constraining the mechanics, does the need for those vertical forces go away, or is it exacerbated in trying to match the deformation signature in the continents? And I think that can only be helped by getting a much tighter constraint on what that vertical signal actually is. So yes, absolutely. I think that it will help, but I think it's not an easy fix to the problem. Great. Thank you. Thank you.